I think that over 95% of the major lunar surface features are volcanic in origin. That is, all of the maria, all of the mountain ranges, most of the rays, and most of the craters are of internal origin. Nevertheless, we have to be aware of the fact that the moon has been bombarded by meteorites, and there must be impact craters on the moon, just as there are on the Earth. But the dominant process, the overriding process, is probably volcanism.
I think that most of the craters on the moon have been formed by impact, by high-speed solid objects in space that hit the moon, and by flying bits and pieces of the moon itself. There's no doubt there's been volcanism on the moon, and in fact, most of the rocks on the moon are probably volcanic in origin. But we have to distinguish between the rocks and the craters that have been formed on them. Most of the craters have been formed after the rocks were already in place.
Ever since the invention of the telescope, scientists have been arguing about how the surface features of the moon were shaped. Over 300 years ago, simple experiments showed that the craters of the moon could have been formed in either of two ways. One was volcanic action, an internal process. The other was the impact of solid objects from space, an external process. One of the most prominent craters on the moon is Copernicus, 8 times as wide as the Grand Canyon and twice as deep. Copernicus is typical of lunar craters. On the floor is a group of central mountains. A series of terraces makes up its inner walls. The outer flanks of the crater have a hummocky or lumpy appearance, and many small craters dot the area around the main crater. A system of rays, or light-colored streaks, extends for several hundred kilometers in all directions. Volcanism or impact? The controversy continues.
To me, Copernicus is a typical caldera. In other words, a large basin of volcanic origin. I've come to this conclusion by the study of calderas and other volcanic features on the Earth. A caldera forms when a large volcanic area subsides or collapses when the underlying molten rock or magma is withdrawn or drains away. It's a slow process and takes many thousands to hundreds of thousands of years to form. All during this time, however, volcanic activity continues, and many volcanic features form which are typical of calderas.
One of the ways that scientists try to solve problems is by use of analogies. That is, looking for features on the Earth that might resemble features on the moon. One of the obvious things to do is to look for impact craters. This is the best-known meteorite impact crater in the world, Meteor Crater, Arizona. The crater is actually relatively small, a little less than a mile in diameter. But now notice that building on the rim of the crater. It's about 100 feet long, just about the diameter of the meteorite that formed the crater. The size of the crater gives you some idea of the energy released by impact of even a small object traveling at the very high speeds of meteorites. Around the rim, you can still see quite clearly the hummocks, or low hills, that have been formed by great clots of debris that have been deposited on the pre-existing surface of the ground. Another important feature is the shape of the crater itself. In this and in all other impact craters, the rim is higher than the surrounding terrain. The floor of the crater is below the level of the surrounding terrain.
I must admit, lunar rays are a weak point in the volcanic argument. If we look at the rays closely, you'll find that there are more craterlets on the rays than there are between them. How can we account for this? Well, possibly they may be equivalent to fractures, such as the one that I'm in here. We know that on the Earth there are very extensive fracture systems extending for thousands of kilometers. On a smaller scale, we see many examples on the Earth of where fractures localize volcanic activity. A fracture like this one is actually a weak zone in the Earth's crust, and as you'd expect, there's a great deal of volcanic activity along this rift. As a result, there are now many small volcanic features, domes, craters, cracks, and small lava flows, all lined up along the fracture. So therefore, I think the linear rays on the moon, in part, could be caused by fractures in the lunar crust. The small craters could be volcanic in nature, and the light-colored material could be recently exposed volcanic ash and dust.
The rays and the small craters around Copernicus have a simple explanation. They're formed by great masses of material that's thrown out of Copernicus and lands some distance away. To understand that mechanism, let's look now and see what happens during an impact. Shallow underground explosions have an effect very similar to that of impact, and they help us to understand the impact process. Huge quantities of material are ejected and are broken up by the friction of the air. On the moon, where there is no air, these clots will hold together and will land with most of their mass intact to form many other craters, which we call secondary craters. Here is the crater formed by the nuclear blast, which you've just seen, and it shows a typical hummocky terrain, and a little distance away you can see swarms of small secondary craters that are typical of all large explosion craters and impact craters. So you can see that secondary craters are formed by huge masses of rock ejected by the impact. Each mass of rock throws out a small amount of fresh material from the secondary craters to form the rays.
Small craters are very common in volcanic areas. In fact, volcanic terrains and small craterlets more or less go together. And there are several ways you can form them: by steam explosions, by the withdrawal of lava at depth, by the collapse of lava tubes, and finally, volcanic eruptions and explosions will eject large quantities of materials, including volcanic bombs. And when they impact into volcanic ash, they'll form an impact crater. The important thing to remember about these craters is that you cannot tell from a distance whether the craterlets are produced by the impact of volcanic bombs or whether they're produced by the impact of debris thrown out of a meteorite impact crater.
The heart of the problem lies in the distribution of the craters. Around a volcano, the small craters formed by falling rocks are randomly distributed over the flanks of the volcano, whereas around an impact crater, the rocks forming secondary craters fall in a very definite pattern. And we can see that pattern of small craters around the large lunar crater Copernicus. Now, if we look at the pattern of the rays in which the secondary craters occur, they form very definite arcuate patterns on the moon's surface. And down here, we have a large loop-shaped ray with many secondary craters in it. How can we account for this pattern? Another useful tool that a scientist uses is to develop a mathematical model. In this case, we can calculate how fragments may have been ejected from Copernicus and determine the place at which a fragment may have come that has landed to form a particular secondary impact crater.
rocks that are closest to the point of impact initially are thrown the farthest, and rocks which are farther from the point of impact are thrown less far. Now, when we've finished with these calculations and put all the pieces back into Copernicus along the ballistic trajectories, we find that they form a straight cluster originally within the ground where the crater now stands. Now, our ability to explain this pattern by this method leads me to believe that Copernicus was formed by impact.
The craterlet loops around Copernicus show up very clearly. There's no question about it. But we have to be concerned with the shapes of the so-called gouges on the loops. I don't think these loop craterlets are of impact origin. To me, they appear to be volcanic. Let's look at one of these craterlets in detail. You can see that it's actually made up of two or more craterlets that have overlapped or fused. These types of fused and overlapping craterlets are very common on the Earth in volcanic terrains, and the explanation for them is rather straightforward. They're caused simply by the shifting of volcanic activity along a fracture from one place to another, and this results in craterlet overlap. This leads me to the conclusion that the craterlets on the loops around Copernicus are not of impact origin, and I think they're volcanic. So if we believe that the loop craters are of volcanic origin, then the entire loop on which these craterlets occur could also be of volcanic origin, and therefore the large crater responsible for the loop, namely Copernicus, could also be of volcanic origin.
Additional evidence comes from the samples brought back from the moon by the astronauts. They picked up many pieces of rock, some of which were specimens of hardened lava, and these we expected to find. We also find in the samples of soil brought back by the astronauts large quantities of glass, tiny drops and spheres of glass and broken fragments of glass. But if you look at these pieces in detail, you find that they have tiny craters on them lined with glass, craters that have been formed by high-speed impact of very tiny particles in space. And we actually find the traces of the meteoritic particles themselves in this glass. So we have direct evidence then that the very tiny craters, ranging from things smaller than 1,000th of an inch up to craters tens or hundreds of feet across, have been formed by impact from the return samples. Thus, for me, the evidence is very strong that impact is the mechanism that has modified and shaped the lunar surface as we see it today. Not only do the predictions from theory fit, and we find the numbers of craters that we might expect, but the evidence that's been brought back to us from the samples from the moon also fit this theory as far as we can see today.
It's true that many of the glass spheres have small pits in them, suggesting that they have been struck by micrometeorites, which is what you'd expect because the Earth and the Moon have been bombarded by these small objects since the beginning of time. What's interesting is that we find large numbers of glass spheres and dumbbell-shaped objects in volcanic ash on the Earth, similar to the objects reported in the lunar return samples. I think the evidence is quite strong that the dominant mechanism that shaped the surface of the Moon was volcanism in the geological past. Everything fits. The things that we see, the similarity of these features to known volcanic features on the Earth, and the samples returned by the astronauts. And the beauty of it all is that it can be explained by one well-understood natural process, that of volcanism.
One of the places we might go in future missions would be to the central peaks of Copernicus. There is a place we could really test the hypothesis. If I'm right, the central peaks will be a large mass of rock brought up from depth within the Moon, strongly damaged by shock.
One way to settle the controversy would be to go to the central mountains of Copernicus. If Copernicus is indeed a caldera, I would expect that the rocks returned from the central mountains to be ordinary volcanic rocks undamaged by impact.